We'll now study the rate equation with respect to focusing on experiments. So there are two equations that's typically been used. One, the rate equation is equal to the amount of product divided by the time taken, or the amount of reactant used divided by the time taken. The other second one, the concentration of the reactant used is actually equal to the volume of the reactant used divided by the total volume of the liquid mixture. Okay, the first example that we have is to look at the volume measurement by trigonometric method. All right, by trigonometric method, and we typically actually have the reactions quench. Quench means that you slow the reaction down to a negligible rate, and you can try to do that by either adding copious amount of cold water, typically about 4 or even up to 10 times. We can place the reaction mixture on an ice pack to actually slow down the reaction, and at times chemicals are added to neutralize the reactant so that the chemical reactions will cease. So one of the experimental techniques that's used in studying of rate equation is use volume measurement of solution. The second one is to use volume measurement of gas. In this case, you could have calcium carbonate reacting with HCl and then collecting the gas over a span of time. From then, we can actually plot the graph. If the graph ends up as drawn down here, which is a product time graph, then we can make assumption that it is first order, and by knowing the maximum amount of volume of oxygen that could be produced, we can mark a half V0 and 3/4 V0 and check whether the half-life here and the half-life here is constant. If it's constant, it will indicate that the reaction with respect, in this case to HCl, to actually to be first order. Alternatively, if the graph that you get is one which is a straight line graph, then we can right away conclude that with respect to HCl is zero order. But certainly based on the data that's collected, obviously it's not zero order, it is first order since the half-life that we demarcated is actually constant. Let's take a look at another example. The other example is using the formation of precipitate. This is an O-level experiment that we typically do. You take thiosulfate, you add your HCl. From there, you start the stopwatch and then you time what is the time it takes for actually the cross to actually disappear. So in this experiment, we'll design it in a way by using various volume of HCl, thiosulfate, and water added together to make sure that the total volume of the solution is the same. And from there, we can time it taken for the cross to be covered by actually the sulfur that's produced. And from this data that's collected, we can now determine the order of reaction with respect to thiosulfate and HCl. Before we do that, I think the first part to take note is that we use the same cross because the reaction rate is now the mass of sulfur that's produced to cover the cross divided by time taken. Since the same cross is used, Ms is actually a constant value, which means you can estimate your reaction rate by actually 1 over time, which is what we did down here in terms of our calculation. Secondly, we want the total volume of the solution to be 70 cm3. The reason is so that now the volume of your HCl is actually directly proportional to the concentration of HCl that's used. Similarly, the volume of the thiosulfate used is also directly proportional to the concentration of thiosulfate that's been used. So from that, we can work out the mathematical calculations and conclude. And with respect to thiosulfate, is first order, while with respect to HCl, it's actually zero order. Another experimental technique that's used is to observe the color change with the use of actually a light sensor. So in this case itself, in this reaction, as bromine is produced, the solution will start actually becoming orange and eventually becoming dark brown. So in this case, by registering a number here, we will be able to actually sketch a graph, and the graph typically we sketch will be turned as actually exorbance divided by time graph. And in this case, the exorbance time graph will actually be as such. As the solution darkens, the amount of light being absorbed will actually increases. So from this graph, we're able to determine the order of reaction. Finally, we can also study the reaction rate by observing the pressure change. So in this example that we have, we start off with 1 mole of NO and 1 mole of oxygen, and the initial pressure gauge reading of the reacting vessel is 1.5 atm. After 10 seconds, it reaches 1.2 atm. So from this data, we can determine the rate of reaction. To do that, the first thing we need to do, we need an ice table. So to do the ice table, we express them in terms of partial pressure. So the partial pressure of your NO is actually half multiplied by a total pressure of 1.5. So we start off with 0.75. Similarly, for the case of oxygen, it's also half times 1.5. Thereafter, the reaction takes place. We do not know what's the amount. And from there, we can find out what is the final partial pressure that's present for each of the gases, on assumption that minus 2x atm of your NO react with minus x atm of your oxygen to produce 2x atm of your NO2. So one of the data we do know that the total pressure is actually now equal to 1.2. Hence, because of this, we can actually take this number to sum this number plus this number, which is equal to 1.2 ATM, which is what we did. So by doing so, we can conclude that X is actually equal to 0.3 ATM. And once we know X is equal to 0.3 ATM, we know the amount that's chemically converted here. So in this case, with respect to nitrogen monoxide, the amount of NO that has been used up will be 0.3 times minus 2. That will give us negative 0.6. And that's the reason why the average reaction rate will be given as 0.060 ATM divided by, so this is the number divided by 10 seconds, since the pressure gauge readings is 1.2 ATM after 10 seconds. With respect to oxygen, in the same way, is minus X. So that's the amount of oxygen that has been used up. And you divide by 10 seconds, and that will give you the rate with respect to oxygen. Finally, if you were to study the product that's produced, which is actually the amount of NO2 produced, then in the same vein, we'll take 0.3 ATM times 2, that gives us 0.6 ATM here, divide by 10 seconds. So that's the average rate of reaction with respect to NO2. Finally, before we end off, it's imperative that you take a look at the quiz exercise 4, quiz 1 and quiz 2. These are the two most asked A-level questions in the exam. One, we need to learn how to normalize the data. In one of the sample data given, the total volume is no longer constant. In this case, it's 2000 cm3. While in quiz 2, the twist for quiz 2 is that the reactant is in actual fact colored. So as the reaction proceeds, the reactant is actually decolorized to form a colorless solution. Therefore, the reaction rate is in actual fact the number of moles of iodine divided by time. So one has to bear in mind that this is the reaction rate, and our normal assumption of reaction rate being equal to 1 over T may not apply. So in the exam, you need to be able to deal with these two popular questions. In quiz 1, where the total volume is no longer constant, and in quiz 2, whereby the reaction rate is no longer just 1 over time.